So I'm not going to spend 30 minutes or whatever going through the full derivation of why MOSFETs can be used as amplifiers, because it is effectively the exact same thing as our BJT analysis, except using a different type of transistor. Okay? So we are going to skip ahead a little bit and go straight into our small signal model. So the small signal model for a MOSFET looks something like this, where we have our gate terminal. Down here is our source terminal. And up here is our drain terminal. For the BJT, between the equivalent terminals, so for a BJT between the base and the emitter, we saw a diode, which we represented with its small signal equivalent, which was a resistance, R pi. Well, for a MOSFET, we have the gate source capacitance, which has an impedance of infinity. So effectively, we treat the element, I guess you'd call it, between the gate and the source as an open circuit over which a voltage, a small signal voltage, VGS, appears. Okay? Now, capacitors, as I hope you all know, do have an impedance at particular frequencies. And so when we start to look at the frequency response of transistor circuits, which is a big part of ELEN 336, we're going to update our model accordingly, but we're going to have actually a lot more than that one single capacitance to concern ourselves with. But for the time being, we are going to consider that we are analyzing our circuits at a point where the external capacitances used to bias the circuit are large enough so that they behave like short circuits at our frequency of interest. And we are going to assume that the internal capacitances of our MOSFET are small enough such that they behave like open circuits at our frequency of interest, okay? So I know that that's kind of a weird thing because some capacitors we're treating as short circuits and other capacitors we're treating as open circuits, but it all has to do with the frequency dependent impedance of a capacitor. Okay, so we are absolutely going to update this with capacitance later, but for now, let's keep things simple. The role of the capacitor in an amplifier, the MOSFET in an amplifier is to convert small perturbations in the DC voltage operating point into a current flowing through the drain. And so we are going to have a dependent current source given by GM, the transconductance of our MOSFET, which we're going to talk about in a moment, multiplied by VGS, which is our small signal gate source voltage. Sorry, my dentist was trying to call me. And in the presence of channel length modulation effects, we are going to have a resistance that appears between the drain and the source as well. So I'm going to model that with some resistance R naught, and we're going to call this terminal our drain terminal. So the first thing that I want to introduce is the concept of transconductance for our MOSFETs. So GM, which is our transconductance parameter, is the partial derivative of our drain current ID with respect to the quantity VGS, our controlling voltage, which is given by mu n Cox W over L times VGS minus VTH. Now, if you recall, our drain current ID in the saturation region, which is where we want our amplifiers to be biased, is given by 1/2 mu n Cox W over L times VGS minus VTH squared, assuming an NMOS transistor, right? We can use this relationship to come up with a couple of alternative expressions for transconductance that depend on effectively what information we're given. So this first classical definition of transconductance requires us to know what our DC operating point gate source voltage is. All of the other parameters are effectively constants and won't vary from design to design, but VGS is going to depend explicitly on the DC operating point. Well, we can rearrange this guy and solve for VGS minus VTH. So that would look like VGS minus VTH is equal to the square root of twice ID divided by mu n Cox times W over L. And substituting that relationship in for VGS minus VTH into our original transconductance equation gives us the relationship square root of 2 mu n Cox W over L times ID. So this is another way for us to express our transconductance, in this case, when we know what the drain current is, but don't particularly want to know or care about what VGS is. And finally, it can also be written as twice ID over VGS minus VTH. So in the instance that we know what both of those quantities are, or both portions of the DC operating point, we have the simplest mathematical representation for our transconductance. So these are the three different ways that it can be expressed. My default is actually usually this middle one, just because most of the way the problems are set up is we're told what the current is, and that allows us to easily calculate it, and all that kind of good stuff. So for our output resistance R naught parameter, our channel length modulation resistance, I guess would be another way to put it. We get one, so actually, let's see, it's the inverse relationship of the change in ID with respect to voltage VDS, which comes out to be 1 over lambda ID, where lambda is our channel length modulation coefficient. This can, well, actually, I'm just going to leave it like this. There is another representation, but it requires the presence of the drain resistance and all that kind of stuff that I don't want to worry about right now. So this is kind of our default. Let's run with this one. So for a MOSFET transistor, we only have two small signal parameters that we really need to concern ourselves with. All right. So with that taken care of, let's start looking at some amplifier circuits. The first of which is the common source amplifier. So the common source amplifier is the MOSFET version of the common emitter amplifier. So our most simplistic representation is going to look like this, where we have some power supply voltage VDD, a resistance RD. Here's where we take our output voltage. Our source terminal will be connected directly to ground, at least for this core representation. And then here is our input signal. So just to be clear, gate, drain, and source for our NMOS transistor. Okay. So we're going to go through the steps of determining input resistance, output resistance, and voltage gain for this circuit, which means we're going to need to draw our small signal model. So for our small signal model, it's going to look something like this. Gate, drain, source. Our source is at ground. Between the drain and AC ground, we're going to have this resistance RD, over which our voltage drop V out appears. On the input side, here's our input voltage, VN, like so. So by inspection, what does my input resistance for this circuit have to be? Infinity, absolutely right. Because no current is going to flow in. So Vn divided by 0 is going to look like infinity. So we have an infinitely large input resistance. All right. What about our output resistance? So to determine our output resistance, even for MOSFETs, we do the exact same thing. We short out our input voltage source. If Vn is 0, what is VGS? 0. How much current is being supplied by this dependent source? None. So when we look in from this direction, we simply see RD in parallel with R0.
Because the current source is open.
Exactly right. So if the current source is supplying 0 current, then it looks like an open circuit. Absolutely correct. And our voltage gain. Okay. So let's see. Our output voltage is the voltage drop over RD in parallel with R0. The current flowing through that parallel resistance is GM times VGS, where VGS is exactly equal to VN. So let's write this down real quick. So we have V out is GM VGS R0 in parallel with RD. Since the current is flowing into the negative polarity terminal, we need to put a negative sign here. Vn is exactly equal to VGS, which yields our voltage gain equation. AV is equal to V out over Vn negative GM R0 in parallel with RD. How does this differ in any way, shape, or form from the behavior of a common emitter amplifier with early effect included? Our input resistance is different. It's no longer R pi, now it's infinity. In every other way, these circuits behave in the exact same way. Okay. Now, well, let's say they behave in the exact same way on paper. Effectively, we have the exact same way. Now, there is a very important distinction here between the operation of a MOSFET and the operation of a BJT, and that is operation at the edge of saturation, right? So we know that for a BJT, we can really push things 200 to 400 millivolts beyond that edge between those two, and we still effectively get what looks like forward active region operation. Okay? For a MOSFET, that isn't true. As soon as we make VDS less than VGS minus VTH, we push into triode region. So we don't have any grace period, as it were. Okay. So our voltage gain here, and just to be clear, this is the expression that I'm expecting you to use, apply, etc. But if we plug in our equation for GM, what we'll find is that we have negative the square root of 2 mu n C ox W over L times ID. All of this multiplied by R naught in parallel with RD, which tells us that our voltage gain is dependent both on our drain current and the size of our resistor RD. If either of those two quantities increase, the magnitude of our gain goes up. Well, as the magnitude of our gain goes up, we are more and more likely to push our device out of saturation for a portion of the input waveform. Okay. So for this circuit to remain in saturation, looking at it, we can see that VDD minus RD ID, which is simply the voltage VDS, needs to be greater than the quantity VGS minus VTH. With a little bit of math, we can see that the product of RD and ID must be less than VDD minus VGS minus VTH, again, to ensure saturation region operation. So there's absolutely a trade-off here that we experience, right? And this is called a headroom constraint. The more we increase our gain, the more likely we are to push our device out of saturation. And it comes from the fact that we have this DC current ID flowing through this DC resistance RD, generating effectively a potentially, the higher the gain is, the more voltage drop we see there, okay? So we're limited by our power supply voltage as to what our output, the maximum gain that we can achieve is, okay? Now, to get around this headroom constraint, circuit designers have come up with a couple of interesting solutions. The first of which is to bias the amplifier with a current source load instead of an actual resistor. Common source with current source. Look. So what this circuit looks like is this. We have our power supply voltage, VDD, and then we are going to use a PMOS transistor as a current source. So if I apply a DC voltage at the gate and have a DC voltage at my source, VGS is a fixed quantity. So as long as I'm biasing this guy correctly, this PMOS transistor is going to push a fixed amount of current through the rest of my circuit. So it's behaving like a simple current source. On the bottom is where we're going to have our common source amplifier stage. So here is V in, here is V out. I'm going to call this transistor on the bottom M1, where this terminal is source 1, this terminal is drain 1, and this terminal is gate 1. And then I'm going to call this transistor M2, where this terminal is drain 2, this terminal is source 2, and this terminal is gate 2. All right, so let's look at our small signal model. I am going to put my gate here. So this is terminal G1. This is what I'm going to call VGS1. Here's GM1, VGS1, and including the effects of channel length modulation, we're going to have resistance R01. Oh, goodness. And let's see, this is source 1, which is grounded. This is drain 1. And here's my output voltage. Yeah, so that's the bottom half of this circuit. Everybody okay with that? Now I'm going to draw my small signal model for my PMOS transistor. So for a PMOS transistor, we know that the source is at the highest potential. So I'm going to draw my source on top. Up here. So this is source 2, and it's connected to AC ground. This is my gate 2, and this is representing my small signal voltage VSG. Here I have my current source, GM2, VSG2. Let's talk about the direction of this guy. So in a PMOS transistor, does the current flow from the drain to the source or from the source to the drain? Source to the drain, right. Up from point of high potential to the point of low potential. So our arrow is going to be down, like so. And if channel length modulation effects are included, we'll have our resistor R02 here. And this is representing drain 2. And the drains of my 2 transistors are tied together. Finally, I have my input signal Vn. Okay. So what is my input resistance? Still infinity. My output resistance is going to be a little bit more difficult to quantify here. And I actually have made a mistake here that you guys didn't catch. What should my gate terminal G2 be connected to? Ground. Because V bias represents a DC signal. Right? So how we're going to approach this is effectively, we're going to have some resistance that we see looking down and some resistance we see looking up. And those 2 resistances are connected in parallel because they both represent a resistance seen from this node with respect to ground in both cases, right? So what do we see looking down? So we're looking in through this terminal and looking in this direction. What do we see? R not 1. There is no RD at all. But yeah, right? So with Vn shorted out, this current source looks like an open circuit. And so when we look down, literally the only thing we see is R not 1. What about when we look up? So we're looking in through this terminal and looking this way. Just R not 2, right? Because obviously VSG2 is 0 since it's grounded on both sides, meaning that this dependent current source looks like an open circuit. And so all we see is R not 2. From that, our output resistance is simply R not 1 in parallel with R not 2. So from the amplifier perspective, right, so from our small signal perspective, this current source connected load just looks like a resistor RD having a value of R not 2. So from the small signal perspective, we effectively have the exact same circuit as we had a moment ago. We're just going to replace RD with R not 2. So from that, what should our voltage gain be? Negative GM1, because that's the transistor that's performing the amplifier operation, times R not 1, which is the output resistance or the channel length modulation resistance of transistor M1, in parallel with R not 2, which is the output resistance of transistor M2, which is fulfilling the role of RD in our small signal analysis. Okay. So, in short, whenever we're loading with a current source, all we're going to see is the channel length modulation resistance of that transistor. Okay. So anytime we're looking into the output terminal of a current source, all we see is R0. It's going to pop up over and over and over again, which is why I'm making a point to describe it. Okay. How did you guys feel about this analysis? Pretty straightforward. I tend to agree, but we'll see what you guys say. All right. Another possibility here is to load our transistor with or load our amplifier with a diode connected transistor instead of a resistance. Okay. What's going on in chat? Okay. So for a current source load, we applied a fixed bias voltage in order to force a specific amount of current, DC current, to flow through our device, which creates our DC operating point effectively. Okay. A diode connected load is a slightly different perspective. So in the previous example, we had a PMOS transistor up top. Okay. This time we're going to have an NMOS transistor up top, meaning that this, if this is transistor M2, I'm going to call this S2, D2, and G2. And I am going to connect my gate directly to my power supply voltage VDD. And then down here is my amplifier stage. Where I apply V in. Here at the drain, I take V out. Where if this is transistor M1, this is D1, this is S1, and this is G1. I'm actually going to move this over a little bit on my screen so that I can draw the small signal model more easily. So let's talk about something real quick here. What is the operational state of transistor M2?
So VDG is,
Right.
yes, it's greater.
So VDS is a non-zero quantity. Let's assume it's a non-zero quantity. Technically, if we tied V out somehow to VDD, that would be a zero quantity. So let's assume that that isn't happening. Okay. So VDS and VGS are the same thing. Because the first letter of the subscript is corresponding to VDD in both cases, right? That's our top voltage. So we have VDD minus V out is equal to VDS and VGS. Okay? So I would argue that in this configuration, the device will always be in saturation because VDS is equal to VGS, which will always be greater than VGS minus VTH. Okay. We have transistor M2 up top, guaranteed to be operating in the saturation region. If we draw our small signal model, I'm going to start with my transistor down here on bottom. This is node G1. This is node S1. Here is GM VGS1. Here's VGS1. Here is R01, excuse me. Here's my output voltage, V out, and this terminal is obviously the drain of transistor 1. Stacked on top, I have an NMOS transistor. So I'm going to have a strikingly similar small signal model where this node is S2. Here I have GM2, VGS2. Here I have R02. This node up here is the drain 2, and my drain node is connected to AC ground for transistor M2. My gate node is connected to ground for transistor M2. This is my quantity VGS 2. All right. And then over here on the input side of transistor M1, I obviously have my voltage VS. And my source for transistor 2 is connected to the drain of transistor 1. So I'm going to tie those two nodes together. How do we feel about this small signal one? I, again, tend to agree. Well, are you guys doing the best? All right. So we're going to approach this problem in much the same way as we did the last one. Our input resistance is going to be infinity because it's going to be infinity anytime we're looking into the gate. We don't really have a choice on that matter. I say that unless we connect a resistor or something in parallel to the gate, which will mess things up. But anyway. So Rn is equal to infinity. Did I write infinity or 0? Okay, I wrote infinity. Just want to make sure. So we're going to look down. We're going to look up. Those two quantities are in parallel to determine our output resistance. What's R down? R not 1, the exact same thing it was in our last example. R up is a little bit harder this time. Okay. Why is it harder? VGS is not 0. Absolutely right, which means this guy right here is no longer an open circuit. So we have to take into account what's going on. So the current flowing through this element, this dependent source, is GM VGS2. Can we all agree on that? It's literally written right there. We don't have much of a point. That's the whole point of that dependent current source. Okay. What's the voltage drop over that element? VGS2, right? So let me make it super obvious for you guys. Since the gate 2 or G2 node is at ground and the D2 node is at ground, I can connect these two nodes together with a short circuit without losing any information whatsoever, right? So we can easily see then that the voltage drop over this element is VGS2. Now that's actually pretty convenient for us, okay? Let me explain what I mean there. if the voltage drop is VGS2 and the current is some constant of proportionality times VGS2, this guy is behaving like a resistor because there is a linear relationship between the voltage and current through the element. What's the value of that resistor? 1 over GM2, because GM2 represents the transconductance, or a change in current over change in resistance, whereas change in current over change in voltage, whereas a resistance is a change in voltage over the change in current. So this guy right here looks like a resistance 1 over GM2, and it is in parallel with R02. So from that, what is our output resistance? Absolutely right. R up in parallel with R down every time. So R01 in parallel with R02 in parallel with 1 over GM2. So Bailey, what's my voltage gain going to be? Negative GM, is it going to be GM1 or GM2? GM1, right? So transistor M1 is the amplifier in this case because we're applying the input for transistor M1 and we're taking the input out of terminal transistor M1. Multiplied by that output resistance again, right? R01 in parallel with R02 in parallel with 1 over GM2.
Why is VGS2 not zero? Or why is it?
So this node is obviously 0. S is the out, which if our output is the out, we're going to have a pretty crap, or if our output is 0, we're not doing a particularly good job at amplifying. Right? Yeah. Okay. All right. So in the following examples that I'm going to work, we're going to go back to a resistor implementation of biasing these guys with the understanding that I can replace literally any of these resistors with either a current source connected transistor or a diode connected transistor, which we now know what they look like at a small signal. Okay. So for a discrete amplifier, like one that we would build on a breadboard, chances are we're going to wind up using actual resistors. For an integrated circuit amplifier, one that we would design monolithically on a single silicon wafer, we'd actually probably use one of these representations to build our amplifier because it will take up physically less space and give us better performance. Because the reason why we use these guys is because they behave effectively the exact same way as a resistor does, or a combination of resistances in this case, at small signal, but at large signal, they don't cause that large voltage drop that a DC current flowing through a DC resistor will, okay? Which gives us more of what's called headroom. And for those of you who suffer through ELEN 438 with me next fall, we'll go into gobs and gobs of detail about trade-offs and all that kind of stuff that we can do. All right. So let's talk about a common source amplifier with source degeneration. So here is our resistance RD, which again could absolutely be replaced by a PMOS current source or an NMOS diode connected transistor. We're going to take our output here. Here is our resistance RS, which can be replaced by a NMOS current source or a PMOS diode connected transistor. Small signal model is going to look like this. And for now, let's neglect channel length modulation. That should be G, S, D. Here's RD. Here's the end. All right. Jace, what's our input resistance? 110. Nothing particularly difficult there. Okay. For our output resistance, now we're actually going to have to do a little bit more than just look at it to see what's going on, right? So with our input terminal shorted, I'm going to depict like so. What this winds up doing is putting our voltage VGS to be the drop across this resistor RS, positive polarity on bottom. Right? There's a negative polarity terminal is associated with this node S, and the positive polarity terminal is associated with ground. Are we all okay with that? All right, so let's, for the sake of argument here, do this the right way and throw a test source on. Where this is our current I test that we are trying to find. So I test should pretty obviously be V test over RD plus GMVGS using Kirchhoff's current law at our drain node. Everybody okay with that? Well, what is VGS going to be in this case? The current flowing through the source, so GM VGS times RS on the negative side, right? So I'm going to put VGS right here. Let's work our way through this, okay? So we have I test is equal to V test over RD to GM VGS. All of that seems legit. Actually, yeah, no, let's leave that like that. Sorry. Okay. Sorry, I'm getting confused by my notes here because I have VGS is equal to negative I test times RS, which I don't necessarily agree with. Should have looked at this beforehand. All right, so let me think about where my head was at when I did this real quick. Couldn't tell you, my notes don't make sense to me, so we're gonna have to roll them. Okay. All right, so VGS, let's see what falls out of this thing. VGS is going to be equal to RS times GM VGS times a factor of -1. Well, that's just going to give me 1 is equal to, so that relationship doesn't help. Okay, well, that's a bit of a pain in the ass. What else can we do here? Why do I, sorry, having to think out loud. All right, you guys are going to help me troubleshoot this. I have written on my notes that VGS is equal to negative I test times RS, which doesn't make a particularly great amount of sense to me because I see that as no current is being allowed to split off and flow through the resistor RD for that to be true. Now, I could mess with this slightly. And so what I mean by that specifically is I could use that trick that I've used for the past couple of examples to where I have a current flowing, or excuse me, a resistance that I see up and a resistance that I see down. My only concern there is that I'm not including the output resistance or the channel length modulation resistance of my transistor.
Okay, so let's start. What we started with,
I'm sorry, what was that?
what we just assumed, yes. That's basically what
So if we were to assume VGS to be 0, our output resistance would just be RD. But why would we make that assumption? Because there's nothing explicitly stating that this terminal is grounded out, right? So that's the issue. So it's so succinct in my notes and probably so very wrong. There's got to be something super obvious that I'm overlooking. Right? Okay, so that's the negative polarity terminal, that's positive polarity terminal, so that is for sure VGS. So I could say, all right, let me do something here real quick. VGS over RS is equal to negative GM VGS. That's pretty much the exact same relationship that I had a moment ago, isn't it? Yeah, so VGS is equal to this guy over here on the right.
S is equal to, with your voltage shorted, VGS for the voltage at the source, which is caused by the current source forcing a current at voltage drop over resistor RS.
Right, but I feel like that's summarized in these two identical equations right here. Oh,
Do we have a voltage drop across the current or the voltage control current source? The same relationship as it was earlier.
so in this case, that voltage drop across the current controlled voltage source is going to be VDS, which is simply VTest minus VGS. Or excuse me, VTest minus negative, so VTest plus VGS. Let's run with that actually. We're not going to get as far as I wanted to today because I can't understand my own notes, but it'll be okay. We're learning. So what Donald suggested, or at least what I interpreted his suggestion to be, was that this voltage right here, VDS, and that would be, no, I don't know how that would help us though, actually, now that I think about it. Oh, this is frustrating and embarrassing. All right. So here's where I'm gonna. Oh, does that help? Not necessarily. Sorry. So what I was thinking about doing here, I'm just throwing the kitchen sink at this guy, is to say this current would represent I test minus V test over RD. And from this, let's see, this is the thing that I don't necessarily agree with, so I'm going to take that off for right now. from this, we could say that VGS, my thing will write, is equal to negative RS times I test minus V test over RD. Does that sound reasonable? Anybody see anything particularly wrong with that? So this is the current I test. Some of it splits off and flows through this resistor RD, which I'm going to quantify as R test over, or excuse me, V test over RD, which means the remainder of the current is I test minus the bit that branched off. What that did was allow me to write VGS only in terms of I test and V test, which I can then substitute into here, and I will have an expression only in terms of I test and V test, which is what I want to get my output resistance. So let's see what happens. So I get I test is equal to, oh goodness, well, we'll just see, but I feel like this is an effort in futility now that I'm looking at it. Plus GM times, oh, well, maybe not. I might have surprised myself. All right, so have I made my algebraic substitution here correctly? Let's start there. Anybody see anything particularly wonky about the substitution that I've made? All right. So let's expand this bad boy a bit. V test over RD. Let's see. Plus GM. All right, so now I'm going to have a negative RS times a negative V test over RD. So that's going to look like RS over RD times V test, right? And that is going to be equal to I test plus GMRS I test, which I didn't give myself quite enough room. Are we all okay with this level of algebra? We're just throwing crap at a wall and see what sticks. You guys are very brave for actually writing things down right now. Okay, just with you. All right. So I've isolated I test and I've isolated V test, which if I've done my algebra correctly, I know you're laughing your ass off at me for being a jackass. It's okay. I can factor out a common term of I test on the left-hand side. I can factor out a common term of V test on the right-hand side. And so what that's going to give me is I test times 1 plus GM RS is equal to V test times 1 over RD plus GM RS over RD. And I am going to lump those two things together to make this a little easier on myself. So let's call that 1 plus GM RS divided by RD. Which makes it seem like the result is just going to be RD, huh? Yes, what did I screw up, Jordan? Huh?
So going back to setting 0, like I said earlier, so just think about it like the current source going into.
Uh-huh.
Separate everything else out. VGS or VGS just from bottom to the top of the resistor, like it's there. If you have a positive current for VGS positive, now since you're not forced current to the resistor, right? That'll make VGS negative, right?
Okay, so I see. So you're saying
So of course it's itself easier.
quite possibly, yeah.
What's the only valid solution?
And so your suggestion here is that if we had a positive quantity VGS, this would force some amount of positive current through this resistor RS, giving us a positive voltage drop, which would conflict with the polarity of this. I don't see anything wrong with your assumption there. And also, I think we're about to find out in literally just a moment that when I divide V test, or when I do the algebra here, so V test over I test would be 1 plus GM RS multiplied by RD over 1 plus GM RS, which is just RD, which is literally the exact same result that we would get for VGS is equal to 0. So let's stop here so that I can get my head out of my ass prior to Friday's class.